Hey everyone. So I know the last one went over a little bit. I'm going to try to keep it short and open it up for questions at the end. So if you have any questions throughout, you can tweet at me. I'll probably just answer them later offline or in person. But so this is a talk about machine learning on massive streams of data. And this being an Internet of Things conference, I wanted to kind of give the use case of why do we need to do machine learning on such a large amount of data? Why even use this for certain types of data products and applications? And a little background on me. I started off at Berkeley. I did computer science and physics there. So I got to kind of see the instrument kind of, I guess, sensor data coming through. Also did machine learning in the CS department. So it kind of whet my appetite. After that, I worked at a company called Alpine Data Labs, basically building machine learning applications on distributed systems, most specifically Hadoop. So I got to see firsthand what it's like to try to distribute a complicated algorithm. And now currently, I'm at a place called Zipfian Academy. I'm the co-founder of a school that teaches data scientists and data engineers in immersive 12-week programs. So it's a full-time 8 to 10 hour a day, 5-day a week, 12-week program, really geared towards people who want to get into data science, data engineering, software. So we cover everything from programming in Python to machine learning to data viz. So we kind of try to cover a large breadth of topics. But the topic at hand, Internet of Things. So you're all here. I'm sure you know why the Internet of Things. There's devices like Nest, Google Now, there's Jawbone and other quantified self devices. There's also things coming out now that control your home, like Electric Imp and some smart devices from Belkin and GE. GE also measures a lot of industrial applications. This is some of the most exciting applications, I think, of machine learning for me, at least, just because the benefit to make sure a turbine doesn't fail. And fun things like this. If anyone hasn't heard of this, it's like a Fitbit for dogs. So it's everywhere, and why and how. I like to put them in two groups. There's the Internet of Things devices that connect your life, connect your devices. These are things like Belkin's Wemo, Electric Imp, the light bulb I showed, and a sensor device called Spotter. And kind of on the other side of Internet of Things devices are things that enhance your user experience, things that enhance your life. Google Now tells you when to go to your next meeting, how long it's going to take. Nest, smart thermometer. Jawbone tells you things on how you're eating, how you're exercising. And then industrial monitoring, preventing large machines from having very costly failures. So this talk is about machine learning, and where it comes into play on this is the enhancement side. While it does probably come into more the connected devices, a lot of these products here wouldn't be possible unless there was some algorithm to give you these automated results, but not only automated, very kind of impactful to what raw data is coming off of them. And the two constraints I like to talk about if you were designing this would be it needs to be responsive, and I say acceptably real-time, meaning it doesn't have to be millisecond. We're not trading on the stock floor, but just for a human, about a second, a minute. And the thing that's unique about Internet of Things that I think other machine learning applications don't have to deal with is these large amounts of sensor, semi-structured data. And most kind of characteristic, it could have many, many features. It could be something where there's hundreds, thousands, millions of features coming off of one or many sensors. So how do we tackle these problems and work on large amounts of data with very complicated feature sets and give these results in very near real time? So people often, I hope they often make this question of themselves of, do I distribute my processing? Do I keep it on a single machine? Do I buy 2 terabytes of memory, or do I buy a bunch of Dell computers and string them up in the cloud? So I'll first tell you why you shouldn't ever do distributed machine learning, part of this is from my experience at Alpine Data Labs and dealing with some of the complexities of that. But also, there's some funny talks out there by some of the creators of these new paradigms to do distributed machine learning where they say just right up front in their presentations that the complexity is often not worth it. And machine learning by itself is very hard to know when you're getting things right, when your algorithm is giving the correct results. You might be going off some pseudocode, you might be going off some reference implementation, but it's somewhat difficult to know where you can't say, my output is 10, it's 90% accurate. I know that that's the right implementation, especially if you're dealing with an algorithm that has some randomness in it, things where you have random starts like k-means, or other sorts of stochastic behavior where it's non-deterministic. You run it 10 times, it gives you 10 different results. How do you know that it's working? And kind of just verifying how correct it is, and then the edge cases. So something unique about Internet of Things, you haven't seen every example that could possibly come your way. So you have to account for what about unseen types of data points with features that I've never encountered before. What do I do in that case? Add on top of that, distributed systems. So this is kind of very characteristic of typical engineering. You have a lot of moving parts, many machines that all have their own internal clocks moving, that you have to synchronize them. You have to make sure that the concurrency and parallelism, especially when you're building a machine learning algorithm that has these very kind of strict expectations of the state at any point in time. And also, distributed systems were kind of designed to be tolerant to failures, which is a good characteristic to have. But what do you do if one of your nodes in your cluster fails when you're in the middle of some optimization with your algorithm? So these are hard. What do you get when you combine machine learning and distributed systems? You get something that's hard to wrap your head around. It's hard to know what strict guarantees you can expect at given points in time. And I refer to Hadoop and Mahout, which are kind of the canonical distributed systems frameworks, which handle a lot of the coordination, but what they don't handle is kind of the design of things. And you often hear, it's just maps, it's just reduces, word count examples, you split up your input data, you do some sort of function on that, and you get some final result. This is great for a certain domain of problems where they're this additive process. You can tolerate nodes going down. You just increment things. Some machine learning algorithms work very well with this incrementing approach. Some don't. There's no clear diagrams for how do I do gradient descent on logistic regression just out there in MapReduce. It's a fairly difficult problem that a few people have solved, but it's not something that I would want to go out and just do for fun on a weekend, or if my boss came to me and said, implement this algorithm for our new sensor network. And just getting all that out of the way, it is a talk about distributed machine learning, so we will talk about how to solve these. So part of the hope is that you don't need to distribute, that your data can fit on a single machine, that you can run a serial algorithm, that when someone implements a new algorithm, writes a new paper about the next latest, greatest neural net, that you don't have to figure out how to then distribute that. Something that's kind of funny is that it takes so much work to put these implementations out there that if someone comes out and says, oh, new benchmark for single machine random forest blows distributed random forest out of the water, you're like, shit, I spent like a year making this thing great, and now I have to spend another year doing it with this new algorithm that is then going to kind of get bested in the next kind of iteration. So to start off, I'm going to talk about the modern data architectures. So these are things typical of data engineering, where you're talking about streams of data, flows, pipelines. What this is the popular Lambda architecture. It's kind of getting a lot of hype. It was invented by Nathan Mars. He's coming out with a book that is pretty much all about this abstraction. And it's not the only way. It's something that I think a lot of people have gravitated towards, because in the top section here, we have a batch process that works on your entire data set. So what's great about this is you never throw data away. So you have your master data set there. You incrementally keep doing these batch jobs. But to get this real-time kind of result to your end user, you also use some stream processing. In here, Hadoop and Storm with HBase in the middle or some other query layer, but it doesn't have to be this way. It's just a good way to kind of conceptualize these things. So you might imagine at the top in the batch layer, you're running just some long train algorithm that might take a week in batch. And once it's done, once it's finished training, you update your data stores with the new trained model. And in your speed layer, the real-time results, you might use an online, less accurate algorithm. You might use something that can increment what your batch algorithm produced. But this is just a general conceptual framework for how do I architect my whole process. And this is also a separate architecture that Jay Krebs from LinkedIn actually came out in opposition of the Lambda architecture, where he's been working on the stream processing engine that LinkedIn uses and made the argument that why do I need two separate things? Why do I need a separate batch system that has a separate processing engine? Why do I need a separate real-time layer? Why don't I take everything as streams, put it through a single processing layer that has the same code base, has the same kind of consistency and guarantees? And in here, he basically lags one. So the batch layer in this architecture is basically lagged however many days you want it. So you have your real-time stream coming in, updating one of your database tables. You have another lagged stream that takes these batch updates, or analogous to the batch updates where it works on the historic data. So this kind of gives you similar guarantees. The distinction between these is more of, I would say, like personal preference and which one you're more comfortable with. But why do we care about these when we're talking about building a distributed algorithm? What is the magic that goes on in the stream processing? Everyone has some database. Everyone has some message queue. In this case, it's often Kafka that is kind of this message bus that can ship data to any number of sources. And what goes on in the stream processing system is what I like to refer to as more the machine learning architecture as opposed to the data engineering, where this is very typical of what you're seeing come out of a lot of companies who are writing blog posts, who are getting their frameworks out there, where you have your application that takes your raw data in. You have your machine learning service. So this is all API, service-oriented architecture that does featurization, does some preparation. And then you have some scoring server that has your model. And here I drew it as testing, training, validating, all encompassed. But you could split this up. It's the main distinction to make is you have your separate kind of data processing machine learning service from what's giving you your predictions. And here is where a lot of these new architectures for how do I distribute an algorithm itself. So we've kind of walked one step further down, going from high-level data architectures to more specific machine learning API structures. And what goes on in here, one way you can implement things is to just have this continuously training model. Google actually wrote an interesting paper about their ad predictions, that they have so much data, they have a massive distributed decision tree that takes weeks or a week to train, and that might seem like a problem. You need these sub-millisecond results, but the kind of cleverness of the engineers over there is that you can continuously train this thing. Once a week cycle of training is done, you can then put that as your new model that's giving predictions. And as long as your model gives very quick test or predictions in sub-millisecond time, it doesn't matter that it takes a month to train your algorithm. It might be slightly stale. It might be trained on month-old, week-old data, but it gives approximate and good enough results. And here, kind of the distributed nature of things. This is very abstract. You have servers and clients. You can have a kind of master slave or master worker, which is typical of a system like Hadoop. But in the generic parallelism, you have some main coordinator. Here it's a single server. You can have a multi-master type of configuration. And you have a bunch of these clients. So in Hadoop, each of these would be kind of a task worker where it processes a little bit of your data, doing some update, which then communicates with the master in the end of a MapReduce job. This is just going to be where you're doing your job tracking or where you get your final reduce. So masters and workers. And often to make machine learning work on this type of system where you have a single master and many workers, many masters, many workers, I think it's helpful to think more in the abstract that a generic algorithm, you basically have your input data, you have some labels, you have some non-parameterized functions. So this is a linear logistic regression perhaps. And what you're looking to get out of this whole processing and training is your parameters. So this is kind of the key to the end of all this pain and headache. What the example I'll show up here, simple logistic regression. You're looking for these beta coefficients that describe how you're going to actually make your prediction. So this is a very simple equation. This gives you your prediction, but finding these right coefficients is kind of where all the magic comes from. And a lot of the distributed architectures for doing this processing basically coordinate over parameters. So they don't coordinate separate algorithms. They don't build ensembles. They have their parameters and divvy it up on their machines. A few ways to do this is stochastic gradient descent, which works. It can work on a single machine and basically looks at one point every step of the iteration and gives you something that's not the optimal convergence. It gives you something that's good enough and goes much quicker. Feature hashing is something that allows you to do online learning with your stream of data coming in, where you don't have to have all of your kind of vocabulary or your feature matrix or your mapping from input data to output feature matrix values. You can essentially, with feature hashing, if we're thinking of vectorizing some input data, you run some hash function that could be generic, could be specific to your domain, and the hash function will give you deterministic results for a given input data space to your output space, with the benefit that it can happen without storing all your data, without storing all of these mappings. So you can do this online feature engineering, and then just generic incremental updates. This might be something where it's something like mini batch. It might be something where you have an algorithm that is naturally suited to stream updates, like naive Bayes. You simply just have to take some counts and things update and work fine. Valpol Rabbit is probably one of my new favorite frameworks out there that kind of really takes the whole online stream processing to heart and uses a whole variety of techniques, one of which is the feature hashing. One is the stochastic gradient descent. It makes some smart approximations and also has a distributed mode. So Valpol Rabbit has both single machine, potentially multi-core, or a distributed mode that you can run on a cluster, so it gives you the best of both worlds. And just start to wrap things up here. So this is a table of some of the newer approaches out there. There's a few different architectures. All-reduce is what Valpol Rabbit uses. There is a paper that came out of, I think it was MIT, called Hogwild, which is basically, in these columns you have kind of what guarantee of correctness or consistency do you have, and how does the performance vary with that. And Hogwild takes this very interesting approach that basically says, don't enforce any consistency, just distribute all your data, take these parameters throw them out there, split up all your machines, and give them small batches of data, and have this shared memory. So you have a single master with shared memory where each of these machines just updates the parameter it needs to, the kind of value it needs to, without checking any of the other machines, without checking any of the kind of locks. So it's a lock-free update, and performance is basically as much as you can get. Once you drop all kind of consistency or constraints, you can basically just throw as much kind of machines at it, and it'll, in theory, linearly scale. The downside is it would be slightly less accurate, but the paper actually proves that it's fairly good in these sparse matrix kind of problems where, since all your machines are updating one little pieces of it, as long as your data and kind of your parameters are sparse enough, they're not going to overwrite so much that you're going to get inconsistent answers. So it kind of leverages this interesting statistical property of sparse data and not kind of stepping on each other's feet. All reduce has varying levels of consistency, but it's often, I like to think of it as a stricter consistency where it basically is similar to a MapReduce model, but it broadcasts updates to all nodes. Think of sending updates to all reducers at once. They all have this shared state, something like the distributed cache, where they can all read from. Iterative reduce, a similar take on MapReduce. So some of these are improvements on MapReduce. Some of them are completely separate. So iterative reduce is just a more abstract formalism. It's very similar to bulk synchronous processing. So having a bunch of these super steps, but not enforcing any sort of constraints on how it communicates between them. And it's fairly easy to program in this model since it does have some constraints and is usually much better than MapReduce for, as its name, iterative algorithms. So things where you need to stream the output of one step of your MapReduce to the next. So this has an arbitrary number of steps where you can pipeline results. And the last one here that I think's pretty exciting, it's coming out of Carnegie Mellon, called the parameter server. And it tries to do a little bit of all these. So you can tell it how much consistency, how much locking, how much guarantees you want. And it has this tunable performance. So similar to what I mentioned before, where these parameters are kind of the goal, but we're trying to get, the parameter server has this master-master and or multi-master, multi-worker type of setup where each master, each worker is dealing with a certain number of the parameters you're trying to update, and it uses an intelligent scheme to kind of guarantee something similar to eventual consistency. And you've seen a lot of, or you see a lot of these types of approaches come out of database theory. So things like Amazon's Dynamo, where you make these updates and eventually they'll all communicate and give you some consistent state. But you could potentially read from the parameter server in the middle and get some inconsistent state. But given the tunable performance, you might want to optimize for very fast results with kind of approximate accuracy. And just to wrap up, that's where the great user experience, that's where Google tells you you have to leave now because there's traffic and it takes 20 minutes to get to the next place via the Uber you're about to get into. So kind of feeding this scoring server predictions back to the service, which then talks to your application. And just wanted to give a slight kind of mention of the programs that we often offer at Zipfian. So we have a data science immersive and a data engineering immersive. Everything I talked about is very much more characteristic of our data engineering immersive. So if you're looking to get in the field, if you're looking to be a data scientist or data engineer, those would be the key programs. We also have some weekend workshops and more specific topics, and are always looking for people who might want to be instructors, guest speakers, or just get involved in some way with the community. So definitely reach out to me after or shoot me an email. And we're always just looking for more people with cool ideas to either come speak in the classroom, speak at our events, or become more of a full-time instructor. So that's all I have. I think I might have like 1 or 2 minutes for questions, and then I can take questions outside for anyone else who might have them.
So the distributed consistency slide, is that like returning a bunch of weak classifiers and the ensemble of it is better than one, or is this something?
Is it this slide?
No, that one.
Yeah, so this is actually, yeah, so Hogwild isn't an ensemble of weak learners. It's a single learner, but you split up the parameters. So each machine might get one of the betas that it's trying to learn. And it has the effect of averaging things across the parameters, but it's not like the characteristic like ensemble of decision trees or any of these majority vote types of models.
Thank you.
All right, thank you, and I'll be outside if anyone has any more specifics.